Now we're going to look at the first of the two questions to describe motion. The first one is how long. This is the very easy question because there's only one answer, and that's simply time, right? You have to get out of your head that the word long, does not equal length in physics. So long means time. So time is a descriptor of motion that describes how long it takes an object to move between 2 points. Again, the SI unit, so the standard unit that we use in physics is seconds, which we just abbreviate S. And if you get a problem where it talks about miles per hour or kilometers per hour, remember there are 3,600 seconds in 1 hour. Okay, that's the conversion factor between the two. One thing to note that it can never, ever, ever be negative, and that's because for the most part, when we graph in physics, our x-axis is the time axis, which means we're going to graph in the first and fourth quadrants, right? And so if you look at a picture of it, that's when our x-axis is positive, okay? So if your answer is ever negative, I will go to Stockholm, Sweden, and grab you that Nobel Prize, or at minimum, I'll print a copy of one out for you, because then you've discovered time travel. And at this point in time, or at this junction in physics, we're only going to focus on time being a positive value. Okay? So that's the if you want to say the quote unquote easy question to answer, is how long. So just get out of your mind that long means length. All right. So the next question, or descriptor in physics and kinematics, is how far. Okay. So how far actually has two answers. It has a scalar answer and it has a vector answer. But when we really focus on it, we look at it in terms of a position. So a position is when the object has yet to move, or if it changes its position. Okay, and that's just simply the location of an object. Now, if you think about when you were in math class learning how to add and subtract, it was the location on a number line. So +1, +2, -4, all those we can associate back to math, and we talk about in terms of a number line. Okay. Now, when it comes to the end, or when we start now changing the position, we're going to look at really two answers. The first one is distance. The AP test will abbreviate it as X, but sometimes you'll see me write it as a D. Okay, X and D in your mind right now they're the same thing. Okay, and so that's a quantity that refers to the length of a path taken, regardless of its beginning or ending positions. Again, note since it is a scalar quantity, you're not going to have to worry about the sign. So it means it's never going to be negative. It is path dependent, and that's an important thing to distinguish between displacement and distance, is that it does matter how you get there. Okay, and what that really means is it matters if you take a left versus a right, if you go straight versus you turn around and go back straight. So it's just going to depend on it, right? So just of note, there are an infinite distance, right? There's an infinite set of distances between 2 points, right? And that means that you can take extra twists and turns along the way. So like if we're here on campus and say, okay, you're starting in the big gym, and I ask you to go to the office, right? There's an infinite amount of ways that you can get to the office, right? You can go down the different hallways and make different twists and turns. You can actually leave the building and come back through the front door. You can go in a straight line, right? You can go from point A to point B. So note that it's just that straight line is just one of the distances that you can travel. Okay. Now the SI unit, or the standard, is meters. Okay, and just remember, you got conversion factors. There's 1,609 meters in 1 mile, right? There's 1,000 meters in 1 kilometer. Those are just some of the common conversion factors that you may see you run into. Again, if you have anything other than the meters, it needs to go into meters, because that's what all our base derived units are come from. Okay? The next answer, the vector answer is what I should say, is the displacement. Okay, so now displacement is a vector quantity that refers to the change in position of an object, okay? Whereas the distance is the length between 2 points, right, or the path that you take to get there. There's only one displacement, okay? And it's a straight line. And that's really the distinguishing factor between, one of the distinguishing factors between distance and displacement is that there's only one displacement where there's an infinite set of distances, okay? And there's an old country saying, right, that's as the crow flies, right? And what that means is crows have an uncanny ability to fly straight. And so if you ask someone who lives out in the rural areas, they may still use this term. And if you ask them, oh, where's the local grocery store? They may say 10 miles as the crow flies. And what that literally means is 10 miles straight down the road. Okay, if they want you to, if it's something other than straight, then they would tell you, go 2 miles, make a left, at the stop sign, make a right, and so forth. Okay, but if they say as the crow flies, they literally mean straight. And you can Google, there is an as the crow flies calculator or map between 2 points. Okay. So it is path independent, right? So it doesn't matter how you get there. It just matters that you went from point A to point B. So if we go back to the scenario of, hey, we're in the big gym and I ask you to go to the office and I say, okay, now this time walk the displacement, you're literally going to have to go through walls and windows and so forth to make that happen, which would be pretty cool because, then you can, just forge a path forward there from there, okay? Now, because it answers the question, how far? It is in meters, right? It's measured in meters. So distance and displacement, even though they have one's a scalar and one's a vector, they both have the same unit, okay? And it's meters. Now let's look at a couple of examples, okay? And we're going to use our good old number line, kind of from math class when you were learning how to add and subtract. Okay, we're going to look at it 2 different ways. All right. So the first scenario here says an object starts at positive 1 meter and moves to negative 6 meters. And it's asking what is the distance and what is the displacement. Okay, so if we go back to like math class, we're going to start at positive 1, we're going to end up at negative 6. Okay, and so in math class you would have done this, right? You would have counted the humps. In physics, though, we don't count humps, we just put an arrow. And we just try to figure out how big that arrow is. Okay, so if I'm counting the humps, I go 1, 2, 3, 4, 5, 6, 7 humps, which means this arrow is 7 meters in length, right? So that is my distance, 7 meters. Now notice I didn't put a positive or negative sign. I didn't put any kind of direction on it because you have to recall that distance is a scalar quantity and it doesn't matter. Now, displacement, there is an actual formula for displacement. It is your final position minus your initial position because it is change. Remember, this delta symbol, it's the Greek capital D, and it means change in, right? So change in the quantity. So in this case, we're going to change our position. And really what that change in means is, even further, is your final minus your initial. Okay? And so we're going to do our final position minus our initial position. So our final position is negative 6 meters, and our initial position is positive 1 meter. So we have a displacement of negative 7 meters. Now, does it make sense that it's the same length as the distance, or the magnitudes are the same? Yes, because we didn't take any turn along the way. We went straight there. Now, when it points to the left, that is our negative direction. Okay, that's what this means. That's what this negative sign means. It means that it goes to the left, or in our case, right, it goes in the negative direction. Right. So we start out at a positive number, we travel to in the negative direction. Okay, so that's kind of, if you want to say, that's a little bit easier of a problem because we just did one, right? We didn't do anything crazy. We didn't, take a twist or a turn. So let's look at a scenario where now we're going to take a little bit of twist and a turn. Okay, so we're going to start here at positive 1. We're going to go all the way out here to positive 8. So first leg is going to be from here, positive 1 to positive 8, and then we're going to come all the way back to negative 9. Okay. Now, when it comes down to the end, if we want to know the actual lengths, right? This one has a length of 7 meters, and this one has a length of 17 meters. Now, what is that going to help us calculate? It's going to help us calculate the distance. So the distance is going to be that first leg plus our second leg. Oh, I put 12. Apologize for that. Should be 7. Right? So that's going to be a distance traveled of 24 meters. Again, note there's no sign on it. It just means I went 7 meters one way, 17 meters the other way. Or, sorry, I went 7 meters one way, 17 meters and another leg, and that's it. Okay? Now, our displacement is going to look a little different, right? So what we're going to do is essentially, we're going to go from here to here. Because remember, it's delta x is your final minus your initial, okay? And so our displacement is actually an arrow connecting our starting point to our ending point. So we're going to have -9, so we end up at -9 meters. We started at -1 meters, and we're going to subtract those two, and we're going to get -10 meters. Right, so that is our displacement, right? It's -10 meters. Okay, so if you actually count that arrow, so if you count the humps, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the arrow points to the left, and that's our negative direction. Okay, so those are just some 2 quick examples. Now they may go a little bit further and talk about how, what is the velocity and what is the speed. So, we're going to run into that later. That's the third question when it comes down to the end. So right now we're just going to kind of worry about this simple area. Okay. Now here's a couple of practice problems. So kind of same scenario. We're looking for the distance and displacement based on what's happened. So here we're going from. Oh, sorry, I'm panning. I'm not writing. Put the pen. We'll do let's change it up a little. Let's do this little pink color. Hopefully, oftentimes I'll ask, especially a lot if anyone's colorblind. I like to use different colors. So first leg, we go from 0 to 5. So from A to B, then B to C, C to B, and then B to C. Right. So if you want to kind of accumulate what we have here, we got 5 kilometers. We have 4 kilometers. We have 4 kilometers. And we have 4 kilometers. So there we're not taking into consideration right versus left. So then we find the distance traveled, right? The x or the d. It's going to be 5 plus 4 plus 4 plus 4. So it's 9, 13, 17 kilometers would be the distance traveled. Right? So we got 3 segments of 4 plus the 5. Now, again, our displacement. We'll do a darker green, right? Sorry, displacement is going to be our change in x, right? So we're going to do our final minus our initial. So our final position is 9 kilometers, right? Because ultimately we end up over here at C minus our initial, right? And so what was our displacement? Positive 9 kilometers. Okay, so if I were to take an arrow, right, and draw my displacement, it would be a length of 9 kilometers pointing to the right. Okay, and basically what you do is these 2 parts of the trip, the back and forth, cancels out, where it's really only the lengths of these 2 that matter, right? Because when I go back to one spot and I go back to the other, I'm essentially just canceling those out. Okay. All right, so now here's a little, so that's kind of in the same mold, we just didn't do the number line. So here's just another one. Let me bring back just a standard red. Okay, and so we got a physics teacher, you can say Mr. Londot, right? So Mr. Londot walks 4 meters east, right? 2 meters south, 4 meters west, and finally 2 meters north. What is my distance traveled, my displacement? So again, if you notice, like one thing to do that you should start off with is drawing a picture, right? So I'm going to go 4 meters east. I'm going to go 2 meters south. I'm going to go 4 meters west. And I'm going to go 2 meters north, right? And so one thing you notice that I actually just made a loop, okay? And if I kind of take my horizontal right? If I'm at horizontal, my vertical displacements or my travels, okay, what happens is east is the positive, west is the negative, right? So how far did I go horizontally? Well, I didn't go anywhere, right? And if I do same thing with my, my verticals, I go 2 meters north, I go 2 meters south. Well, guess what? Vertically, I didn't go anywhere. So what was my displacement, which is the answer to part B? It's actually 0 meters, right? So what happens is if you go in a loop, right, or a circle, if you just return back to where you start, your displacement is 0. Now, your distance is not 0, okay? So my distance would be the sum of all those little pieces added up. So I went 4 meters one way, 2 meters a different way, 4 meters another way, and then 2 meters again the other way, which tells me in terms of distance, which is my part A, right, I went 12 meters. Okay, so there you can see that once I walk in a loop where I change my direction along the way, my distance and my displacement do not equal each other. Okay, so I often say, and this is a conversation I have a lot with like track athletes and swimmers, right? So I just say that track athletes and swimmers that run complete laps or swim complete laps of the pool, right? They're lazy athletes because they return to where they start from and their displacement is 0. But they're going to argue that they're not because they're saying, okay, I do the 200-meter right breaststroke, okay? Because if you this is where the difference in the definition of the word comes into play, okay? Or the definition that I'm thinking about versus what they're thinking about. Now, I've gotten into lots of arguments with students about this, especially one that says, so when you go home at night, that means you're lazy too because you just go and you park in the same spot. But then I always tell them, no, I'm a physics teacher, so for me to feel like I did something, I actually don't park in the same spot, right? I park an inch up or an inch back, 2 feet up, 2 feet back. I don't park in the same spot every time because this way I'll always have a displacement. I always feel like I did go somewhere, okay?